This is section 5.2 on the topic of matrix representations of linear transformations. And we've seen a little bit about these before, but we're going to dig in a little more here. Let's start here with a theorem to introduce this idea. Let T be a linear transformation, taking elements of U to elements of V. Let U1, U2, all the way through UN, this set of U vectors, be a basis for that vector space U, the domain space. This transformation T, what we really want to say is that this transformation T is really defined completely by its effect on the basis vectors of U, of this domain. So in other words, by the vectors T of U1, T of U2, all the way out to T of UN, right? The effect of our transformation on these U vectors. So what we mean by T is really defined by its effect on these basis vectors is really that anything in the range of T is just a combination of these basis vectors. Right? So in other words, if you know the effect of T on the basis vectors in the domain, you can find its effect on any element of the domain. Right? And this is pretty easy to see the basic idea of if we let U be in the domain, then since we have a basis for this domain, we know U can be written as a linear combination of those basis vectors, right? These U1, U2, all the way through UN basis vectors. But now notice, if I want to apply the linear transformation T to this vector U, T of U is just T of a linear combination of these basis vectors. And by the linearity of T, by definition of linearity of a transformation T, this linear transformation of the linear combination is really just the linear combination of the linear transformations. We've seen this property really defines a linear transformation, is the definition of a linear transformation. Right. So here we've seen that if I wanted to know T of, right, the transformation of any U in the domain, it turns out that it's really just that same linear combination that U was of the basis vectors where it lived. It's that same linear combination, same scalars applied to the images of all those basis vectors. So if I needed A to A1 in the U1 direction to make up my U vector up here, I need A1 in the T of U1 direction. Right? However much of U1 I need that much of T of U1. So this is what this theorem is saying, is that really the effect of T on U really just amounts to the effect of T on the basis vectors of U, as we're seeing here. Okay. So let's see an example. Let T be the linear transformation taking elements of R2 to elements of R3, defined as follows on the basis vectors of R2. So we're going to say T of 1, 0 is 2, 3, 1, and T of 0, 1 is 3, 3, 0. Find T of 4, negative 1. Well, this should be super easy, doing the exact same sort of thing we just saw. If I want T of 4, comma, negative 1, I just need to express 4, comma, negative 1 in terms of these basis vectors 1, 0, and 0, 1, because I know what the transformation gives me from those basis vectors. Just the same idea up here. Break your pre-image, your point in the domain, up into a linear combination of the basis vectors. You'll get that same set of scalars in that linear combination just applied to the images of your basis vectors when you take T of U. So this is easy here. I'm just expressing 4, negative 1 in terms of the standard basis vectors 1, 0. That's 4 times 1, 0 plus negative 1 times 0, 1. I have just broken down 4, negative 1 into a linear combination of those basis vectors that we were given the effect of T on. And we're going to handle this the same way we broke it up in the more general explanation up here. T, a linear transformation, applied to a linear combination, well, we can actually just take the linear combination of the images of those vectors in the linear combination. This is by linearity. Since T is linear, we can pull that move. And now we know what T of 1, 0 is. It's 2, 3, 1. And we know what T of 0, 1 is. That's 3, 3, 0. So we're as good as done. We just put this together. Finish up here. T of 4, negative 1 equals, let's finish it over here actually. Looks like we get 5, 9, 4, just from subtracting these vectors. 8 minus 3 is 5, 12 minus 3 is 9, 4 minus 0 is 4. And there we have it. Knowing just what T does to the basis vectors of R2, we were able to figure out what T does to an arbitrary element of R2. It just so happened we looked at 4, negative 1, but we could figure out what T does to any element, really. In fact, an interesting exercise was T of AB. What is this transformation really doing, right? Let's do it in a general way. If this wasn't part of the problem that was asked about, but it's an interesting exercise, we can do this easily. T of AB is the same as T of A times 1, 0 plus B times 0, 1. And we know that breaks up into A times T of 1, 0 plus B of T, B times T of 0, 1. We can put this together, right? A times T of 1, 0, that's 2A, 3A, A. B times T of 0, 1 is 3B, 3B, 0. So it looks like kind of a definition for what this transformation does is that it takes AB and returns the vector 2A plus 3B, 3A plus 3B, A. That's what this transformation really does. Okay, let's look at another theorem now, theorem 5.5. I guess before we move on, let's notice how useful that is. Knowing just what T does to the basis vectors, we can come up with a general expression for what T does. That's very powerful. So now let's move on to theorem 5.5. Let U and V be vector spaces with ordered bases, B with vectors U1 through U, and B prime with vectors, so I should call these U1 prime through UM prime, respectively. Let T be the transformation taking elements of U to V, then let it be linear. There's a lot to this theorem, so I want to go through it in pieces. First, if U is a vector in vector space U with image T of U having coordinate vectors A, that's the image of this U vector with respect to basis B, and vector B, which is the coordinates of the image under this transformation, but with respect to basis B prime. Then it turns out the coordinates of the image in basis B prime are just equal to the matrix A times the coordinates of the pre-image in the basis B, right? A times matrix A times vector A there. Where that matrix A is really just got columns that are the effect of the transformation on the basis vectors in the domain region, U1 through UN, but expressed in terms of B prime, right? Expressed with coordinates relative to B prime. In the first column, you get the coordinates of the first basis vector transformed under T, but expressed in coordinates relative to B prime. In the second column, you get the image of the second basis vector of B, but expressed relative to B prime, and so on. And we've seen this sort of thing before, where really to know some sort of matrix that represents a transformation, we really just need to know what it does to the basis vectors in the domain. Here we're saying after that, go ahead and express those transformations of the basis vectors relative to the basis you want to end up in. or that you want coordinates to end up in. Right, so let's say here, more in plain language, matrix A transforms the coordinates of vector u relative to basis B, transforms those into the coordinates of the image T of u relative to basis B prime. Just as the actual transformation T takes elements u in the domain and transfers them to T of u in the codomain. Right, what are we really saying here? We're saying we can trade out the actual vectors in these general vector spaces and just do matrix multiplication to transfer between coordinates. Even if it's not a Rn vector space, we can trade out, and instead of looking at the transformation, look at coordinates of some basis vectors relative to these bases. Okay. So the matrix A is called the matrix representation of this transformation. We've seen something like that before. And this diagram here really shows us what's going on here. Right, we can start with the vector u in our domain, and we want to transform it using some transformation T to an element T of u in the codomain. And we could just directly apply that. That certainly is the most direct route to think about it. That's how we've thought about it in the past. What we're saying now is we could just take u. Remember, this u sits in a vector space that is not necessarily an Rn vector space. It could be a space of functions or matrices. But we have some element of some finite dimensional real vector space. And instead of going directly to the image, we could trade out for its coordinates, its coordinate vector relative to some basis of the domain. And instead of doing this transformation T directly, we can apply matrix multiplication, the linear transformation given by matrix A, to the coordinates to get some new set of coordinates that can be traded back and forth with the image vector we're looking for. So instead of working with these kind of abstract vectors directly and transforming between, we trade out for their coordinates and do some Rn type matrix math. It saves us having to think of things in more general terms. You can always reduce down to this Rn, more familiar space, and kind of go around the problem. So as an example, let's let T taking vector space u to v be a linear transformation. And let's let T be defined as follows relative to ordered bases B, consisting of basis vectors u1, u2, and B prime, consisting of vectors v1, v2, and v3. So we're saying U has these basis vectors u1 and u2. The codomain V has basis vectors v1, v2, v3. We're considering these bases. And here we're told what the transformation does to the basis vectors in B in terms of, right, these images are in terms of the basis vectors of B prime. So what do we want to do first? First, let's find the matrix representation of T with respect to these bases. And then we'll find the image of a specific vector. Well, this is pretty simple. This is pretty simple up here. Notice we said the matrix representation, call it A above, is really just these vectors. We want to apply those to that, apply the transformation to those, I should say. Oops. Put one of these in the first column, apply the transformation to the second basis vector in the domain, put that in the second column. You would keep going if you had more basis vectors over here in the domain, but you don't. And the only other little thing is we want this expressed as a coordinate vector relative to the basis we're landing in, the codomain basis. So we want these as vectors expressed as their coordinates relative to B prime, this v1, v2, v3 basis. That's our A matrix. We've expressed just the same way we had up here. So all we have to do is very little here, in fact, because we already have the image of u1 is 3 times v1 minus 1 times v2 plus 1 times v3. That is giving us the linear combination of these basis vectors B prime in B prime, which gives us the coordinates, right, of this T of u1 its coordinates relative to b prime are the scalars we have here. 3, -1, 1. Because t of u1 is some linear combination of those basis vectors. The scalars in that linear combination are the coordinates relative to that basis. By the same token, t of u2 is very easy. -1, 2, -3. And there you have it. There's your matrix representation of t with respect to these bases. Okay, now let's find the image of this vector expressed in terms of the domain basis, u1, u2. So I'll say that was my part A. I'll even sum it up here. The matrix we came up with is 3, -1, 1, and -1, 2, -3. Okay, almost off the page there. Okay. So now we're saying we want to find the image of the vector u under this transformation. Well, that should be easy now, because we know t of u is really just t of 2u1 minus 3u2, right? We know that it's already expressed in terms of these basis vectors. And so this is exactly what this up here is saying. If I know the coordinates relative to the domain basis given, I multiply by this representative matrix A to get the coordinates relative to the codomain basis given, the b prime basis. So my b vectors, what I'm looking for in this example below, we're just going to multiply the coordinates relative to the domain basis by our matrix representation A. So we're going to say a little bit differently here. Sorry about that. Oops. Let me write this a little bit differently. There we go. Now we're specifying that this u is written actually as a coordinate vector of u relative to basis b. Multiplying by a will give you a coordinate vector of the image relative to basis b prime. This is probably the best way to write it. Well, let's think, if we're looking at this vector u, notice the coordinates of u relative to basis b, right? Basis b, let's even back up further. Basis b is just u1 and u2. So the coordinates here are trivial to write down. They're 2, -3. So that's what we should be multiplying here. And what do we have? A little matrix multiplication. Looks like we get 6 plus 3 is 9. -2 minus 6 is -8. And 2 plus 9 is 11. Looks like there we have it. The coordinates of t, of u, the image of u under this transformation, expressed relative to basis b prime is this. And since we know these basis vectors, we know what this is really saying, right? We're saying that t of u is 9 times, remember the basis for b prime is just v1, v2, v3. So we're saying it's 9 times v1 minus 8 times v2 plus 11 times v3. 11 times v3. These are the coordinates relative to this basis, v1, v2, v3. Here is what that vector actually looks like in terms of v1, v2, and v3. Okay, so we found the image of u under this transformation. I guess that was our part B here. I did that, kind of jumped the gun. That was part B that we did. Okay, so let's move on. With another example here, let T be the transformation taking elements of R2 to R3. It's a linear transformation defined by T of xy equals x, x plus y, 2y. The first thing we want to do is find the matrix representation of T with respect to the bases U1, U2, that's in the domain, and U1 prime, U2 prime, U3 prime in the codomain of R2 and R3 respectively, where we are given these vectors for U1, U2, U1 prime, U2 prime, and U3 prime. So we have actual vectors for these U1, U2, U prime, U1 prime, U2 prime, and U3 prime. I should correct this here. These should be ordered bases. Which we write with square brackets. Right? Remember, ordered bases care about which order we list them in the set. Okay. So let's use the matrix. Let's first find the matrix representation of T, and then we'll use that matrix to find the image of a certain vector under this transformation. So let's see. I don't think this will be too bad, but let's figure this out. The matrix representation, that's that A matrix. Remember, that's just going to be the image of our basis vectors, but expressed relative, I guess I'll put these in parentheses, relative to basis B prime, the codomain basis. We want to fill up columns with these images expressed in terms of the codomain basis, coordinates in the codomain basis. So what do we have here? Well, let's see. Well, T of U1 is just T applied to 1, 3. And T of U2 is just T applied to 4, negative 1. So T applied to 1, 3. But we need to express that result with respect to our U3, our prime basis, I'll say it that way, our codomain basis. I haven't expressed it that way. Let's see what we get. T of U2 is just T of 4, negative 1, but that, whatever it comes out to, expressed as coordinates relative to B prime. So what do we get? T applied to 1, 3, remember T is this transformation up here. That's pretty easy, right? So we're going to say this is x is 1, x plus y is 4, 2y is 6. We want that expressed relative to B prime. And the next one, let's see what we get in the next column. We would want let's see. Yeah, 4 plus negative 1 is 3, and 2 times negative 1 is negative 2. We want that expressed relative to B prime. We'll make it a column vector of coordinates. Okay, we want the coordinates of each of these guys relative to B prime. So what do we get here? Well, we're trying to actually write 1, 4, 6 as a linear combination of these codomain basis vectors. That's not too bad though, since this U1 prime, U2 prime, U3 prime is very close to the standard basis. It's pretty easy to rewrite these coordinates. So let's do it. This 1, 4, 6 expressed relative to B prime would be the column vector, right? The coordinates of this guy B prime would be 1 copy of U1. Looks like we would need 2 copies of U2 prime. And it looks like we would need negative 6 copies of U3 prime to make up that 6 there. So we have our coordinates, 1, 2, negative 6. That's this guy. Next one, 4, 3, negative 2. Well, that's also easy. To make the 4 in the first component, we'll have to take 4 copies of U1 prime. To make the 3 in the second component, we'll have to take how many copies? To make a 2, we would need 2/3 of a copy. Or I guess 3/2, sorry. 3/2 of a copy of U2, right? You can see that pretty quick. That would make a 3 in our middle component. And finally, we need 2 copies of U3 prime to make a negative 2 in that last component. Right, so maybe I'll write this out on the side just to make it a little clearer. The coordinates of this guy relative to basis B prime are 4, 3/2, and 2. Okay. So finally, there it is. I mean, there's our matrix representation of this transformation. Now we can use that matrix to find the image of 9, 1. Right, so let's do this. Let's say that the image of T of U expressed relative to B prime, right, the codomain basis, is really just the image of, we want 9, 1 expressed relative to B prime. We know that's just the same as our matrix A times the coordinates of 9, 1 relative to our original basis. Right, remember this is when I write this 9, 1 subscript B here, that's really indicating that this is a column vector. We have to figure out what that column vector is. So maybe we do that up here. We want to express 9, 1 as a linear combination of 1, 3 and 4, -1. Those original U1, U2 vectors. So what do we have? Can we just eyeball this? Let's see. What if we take 2U2 plus 1U1? 2U2 would be 8, -2. 1U1 is 1, 3. Add them up, you get 9, 1. So it looks like I found a linear combination of the domain basis vectors that makes 9, 1. Well, then this isn't so bad. All we need to do is take these coordinates. 1 attached to the U1, the first vector in the basis, and 2 attached to the U2, the second. That gives us our coordinates. Vector 9, 1 expressed as coordinates relative to basis B is this. Oops, sorry, it is 1, 2. That was wrong. And what do we have? Our matrix A, it's 1, 4, 2, 3/2, -6, 2. Now we know we're just multiplying that by the vector 1, 2. And remember, this will be the expression for it relative to basis B. So let's see what we can do here. 1 plus 8 is 9. 2 plus 3 is 5. -6 plus 4 is -2. Right, so these are the coordinates of the image relative to the B prime basis. Well, we were told to find the coordinates relative to B prime. We actually want to know what T of U is, but this is easy now since we know the basis vectors of B prime. T of U has 9 copies of the first basis vector of B prime, 1, 0, 0, plus 5 copies of the second basis vector of B prime, 0, 2, 0, minus 2 copies of that last vector, 0, 0, -1. And just always remember you're going away from the actual domain to coordinates of elements of the domain, transforming the coordinates over, just like the transformation would do to the actual elements, but then you need to go back from those coordinates to an actual vector in your codomain, and that's what we have here. This is just the vector T of u equals keep it quick here. T of u equals 9, 10, 2. Right, and so really what that's saying is T of 9, 1 equals 9, 10, 2. Okay. So let's proceed from there. Let's see what we can do next. Another not definition, example, let D be the operation defined on P2 by really differentiation. So P2, remember, that's the space of second degree polynomials, quadratic functions. D, this operator D, will take an element of P2 and just differentiate it for any element of P2. Any quadratic, this thing just differentiates it. Which does return something else, technically, or more specifically in P1, but P1's included in P2. So this takes P2 to P2. Let's find the matrix of the linear operator D plus 2, defined as D plus 2 of f is the derivative of f plus 2 copies of f. Let's find the matrix of that linear operator with respect to the ordered basis 3x squared, 2x plus 1, 2. Let's determine the image of 6x squared minus 7x plus 4 under this transformation using that matrix. So all we're saying is first, right, here we have something in the actual domain, P2. We're really trying to apply this transformation to see what it produces in the codomain. And so instead of going direct, we're going to go through the coordinates relative to these given bases. We're first going to trade out u for what its coordinates equal. In a theorem above, we called that a, but I'll call that u subscript b, meaning the coordinates of u relative to basis b. And we are going to find the transformation matrix A, so that the result of multiplying A on U, or sorry, A on vector A, is the coordinates of the result relative to the codomain basis. And then we can transfer back if we want to. So this is sort of how we're thinking of it. Instead of going directly through the transformation, we're going to see what is a matrix that does this same thing to the coordinates of these elements without actually performing all the differentiation. So let's see how we can do this. So remember, what we need to do is take the image of these basis vectors and then express those images in terms of our basis vectors. Here we're only given one basis because the domain and codomain are both P2. So we're going to express both domain and codomain as coordinates in terms of that same basis, 3x squared, 2x plus 1, 2, relative to that same basis. So we need to take each of those basis vectors and apply this operator. D plus 2 applied to 3x squared. What does that make? That makes derivative of 3x squared plus 2 times 3x squared. That's what we get. But remember, we need to express this in terms of 3x squared, 2x plus 1, 2, in terms of these basis vectors, right? We need the coordinates of this image relative to this same basis. So if I want to do this, I can just do it by inspection. 6x squared is 2 times the first basis vector, and 6x is, well, it's kind of like 3 times the second one, but then I get an extra 3 times 1 that I don't need. So let me just subtract enough to get rid of it with this 2. I have an extra 3 I want to get rid of. Let me take negative 3 halves of 2. So there we can see now the coordinates of the image of the first basis vector under this operation. The coordinates of that thing in this same basis are 2, 3, negative 3 halves. Now we do the same thing to the second basis vector, 2x plus 1. We take d plus 2, apply it to 2x plus 1. What does this guy make? It looks like it makes Derivative of 2x plus 1 is 2. We add 2 times 2x plus 1. That's 4x plus 2 we add. So 4 plus 4x. 4x plus 4, however you want to write it. But we do need this in terms of these basis vectors so we can find its coordinates in that basis. Well, I'm just trying to match things. You can do this more systematically. I'm trying to make 4x out of the only thing in here in this basis that has a single power of x, and that's the middle basis vector. So I'll need 2 of those. But that just gives me, I have the 4x I need, but that just gives me 2. I better add 1 copy of that last basis vector. 1 copy of 2 will fill it out. Right? You can check this does work. Let me be more specific. 0 times the first basis vector plus 2 times the second basis vector plus 1 times the last basis vector. I have expressed the image of 2x plus 1 in terms of my basis. So I have its coordinates, 0, 2, 1. Finally, apply this to the last basis vector. What do we get? Derivative of 2 is 0, plus 2 times 2 is 4. We just get 4, but again, we have to express this in terms of our basis vectors here. This is 0 times the first one, plus 0 times the second one. Finally, 2 times the last basis vector. So there we have it. That is our transformation matrix, right? Our matrix that represents our transformation. D plus 2 is that transformation. So that is it. How do we actually... I mean, we could very easily answer this next part. Determine the image of 6x squared minus 7x plus 4 under this transformation. In fact, what I'm going to do is way harder than just taking d plus 2 and applying it here, right? D plus 2 applied to this thing. It's pretty easy. It's the derivative plus 2 times the actual function. So I mean, you could write this down pretty easily. That's not really the point here. There it is. That's d plus 2 applied to this thing. What we're trying to see is how do I use a transformation, this matrix that represents this this operator, this transformation, linear transformation. How do we use this to do this same operation? Well, what we would have to do is first express this this vector 6x squared minus 7x plus 4. Again, we need its coordinates relative to this basis. We could multiply those coordinates by a to get the coordinates of the image relative to this basis. So let's do what I'm getting at here. Let's write this 6x squared minus 7x plus 4. Let's write this in terms of our basis vectors, 3x squared, 2x plus 1, 2. So I know I need 2 copies of 3x squared to make a 6x squared. Well, it's getting kind of ugly here. If I want to make a 2x, or if I want to make a negative 7x, I'm going to have to use this 2x plus 1 to do it. There's no other single powers of x available. So I'll take negative 7 halves of the 2x plus 1. That gives me a negative 7x, but it also gives me an extra negative 7 halves I don't want. I need to cancel that with something times the 2 here. So I've got this extra thing I don't want. Let me add something that will take care of it. 7/4 times 2. Right. Believe that looks good. So if I wanted to do this, right, this is really positive 7 halves. So these two cancel out. But I also need this plus 4, so let me add 2 times 2. Finally, I can get my coordinates. You can do this more systematically, but I'm just trying to feel my way through it. So my coordinates are 2, negative 7 halves, and it looks like 7 fourths plus 2, which is 15 fourths. So the coordinates of this guy relative to our basis, I'll call it B, are 2, negative 7 halves, 15 fourths. Now, if we wanted to get the image of the, or the coordinates of the image in the same basis, we say the coordinates of the image, there's the image the coordinates of this thing relative to our same basis are just what I get when I multiply A times this, let's even write it, multiply that by the coordinates of our vector. Notice what you get out there is going to be a column vector that's giving you the coordinates of this image, but again, relative to this very strange basis. Right? So some amount of 3x squared, some amount of 2x plus 1, and some amount of 2 that all add up to be presumably this guy, right? The image we found more simply. That's the interpretation of what this thing does, though. Okay. So I'll leave the details from there. I'll leave those to you to finish for fun. Remember, what you get out of here is just the coordinates of the image relative to the basis B. You would have to actually write that linear combination of these basis vectors out and expand it all to see that it's the same as this simple expression over here. It's going to look like some ugly numbers, some amount of 3x squared, some amount of 2x plus 1, and some amount of 2 that you get out of these this system. It's not going to look directly just like this. Okay. Okay, let's go a little bit further here. Last topic in this section. We're really going to want to see how the matrices relative to two different bases compare to each other for a given transformation. Right? We've seen how to find the matrix corresponding to a transformation relative to a specific basis. But if I had two different bases and I came up with the matrices relative to each of them, how would those matrix representations relate to each other? And that's what we're going to see next. And to see this, we actually have to define something called similar matrices. We have that here with this definition. Let A and A prime both be square matrices and let them have equal size. A prime is said to be similar to A if there exists an invertible matrix C such that A prime is C inverse times A times C. Kind of a strange idea there. We'll see why this form is pretty important. The transformation of a matrix A into matrix A prime by this sort of means, this extra invertible matrix C, is called a similarity transformation. When we take a matrix A and come up with an A prime that's similar to it, we call that a similarity transformation from A to A prime. Why do we care? Here's the big result. Theorem 5.6 in your textbook, it says let U be a vector space with ordered bases B and B prime. Let P be the transition matrix from B prime to B. If T is a linear operator on vector space U having a matrix A representation with respect to that first basis, the domain basis, and A prime is the matrix representation of the transformation with respect to the second basis in the domain for the domain B prime. Then it turns out, how do these two different matrix representations of the transformation relate to each other? It turns out A prime is just P inverse AP, where P is that transition matrix from B prime to B. So we need to unpack this. This is a dense idea. We need to see what it's really saying. The idea in very basic terms is I know how to apply my transformation to basis vectors, or to vectors expressed in terms of with their coordinates relative to basis B. That's my matrix A multiplication will do that. I want to know how would I do that same transformation overall. What matrix would I have to multiply by to use something given in coordinates of B prime? Well, all we're going to do is what I've written here. We're going to see it makes sense that this formula for A prime, that matrix representation representing or relative to B prime, it should make sense why we get this formula. The idea is that we're, in order to apply T, some transformation to an element U, given with coordinates relative to B prime, so that's this A prime matrix we're searching for. Right? To do that, to apply that transformation using this matrix A prime, what would we really have to do to this U? Remember, we're saying U is given in terms of B prime. First thing we would have to do is take U to, right, it's given in coordinates relative to B prime, take it over to coordinates relative to B, because B is the basis that A kind of aligns with, right? A is already in relative to this basis B. So let's take our U and express it in that same sort of basis so it's compatible with A. But we know how to do this. To convert, we need this transition matrix from B prime to B. To take it from B prime to B, we apply that transition matrix from B prime to B. Right? So multiply P times U. Then, now this P times U, that's in terms of the right basis to apply A. So we can apply the transformation just by multiplying matrix A. Right? So we're taking that PU, the thing in the correct coordinates now, and we apply A to it here. That's like applying our actual transformation. But remember, A spits out something relative to B. We wanted something relative to B prime, right? We wanted this A prime matrix to spit out something relative to B prime. So we better take it back. This stuff is relative to B. We take it back, right? Take the result back to coordinates relative to B prime, just using that inverse transformation that took us from B prime to B. All right, use its inverse to go from B to B prime again. So apply at the end of the day an extra P inverse. And we see that really applying T to U by matrix multiplication on coordinates really just amounts to multiplying U by P inverse AP. So we call that the matrix representation relative to basis B prime. We start with something in B prime, end with coordinates in B prime. The matrix that gets us there is A prime, defined just like up here. So I really would think of it as taking it from the wrong basis expression, wrong basis coordinates, to the correct ones to work with A, then apply A and take it back. Right? P takes it to the right basis, A applies the transformation, P inverse takes it back to the basis it started in. That's how I would think about this. So let's do an example seeing this. Consider the linear operator T of xy equals x minus y, x plus y on R2. First, let's find the standard matrix for T with respect to the standard basis. Remember, that's always super easy to do. We just need to, part A here, oops, that is not what I wanted. Okay, let's see. This matrix for this transformation, since it's with respect to the standard basis, this is pretty easy. We're just trying to figure out, right, that's just T applied to these basis vectors. T applied to 1, 0 would be 1 minus 0. And 1 plus 0. T applied to the other basis vector would be 0 minus 1. And 0 plus 1. These are the images expressed in terms of this basis, so we can just fill up a matrix with those columns. 1, 1 is the image of the first basis vector. Negative 1, 1 is the image of the second basis vector relative to this basis. So we know that's our part A matrix that we were asked to find. That's the matrix for T with respect to the standard basis. Now use a similarity transformation to find the matrix with respect to the ordered basis negative 2, 1, 1, 2. So this is exactly what we can use this up here for. To do this, all we really need is the transition matrix from the basis that we want to be in back to the basis we're already in. So we need P, the transition matrix from the basis that we want to be in, this one, to the matrix, oops, cutting it a little close here, I'll give myself some space. There we go. We need P, the transition matrix from the basis negative 2, 1, 1, 2 to the basis, well, the standard basis, right? The one we started in. The one we already have a transition matrix with respect to. So how do we do this? If you remember, this is very easy. Going from a non-standard basis to a standard basis, the transition matrix is just these coordinates filling up a matrix here. Right, you're just trying to figure out negative 2, 1. How can I write that as a linear combination of 1, 0? Well, that's negative 2 plus 1 times 0, 1. Those coordinates are what we're putting here, right? These are the coordinates relative to the standard basis. Vectors are already expressed relative to the standard basis, so it's easy. Well, we know that this matrix we're looking for that's relative to the non-standard basis, that should just be P inverse AP, where we've got P, so we're remembering right away we have to find P inverse. This is pretty easy with a little 2 by 2 matrix formula for the inverse. It looks like we get 1 over negative 5, negative 4 minus 1, times this matrix. You can check my work there on that little matrix inverse, but I think that's what we get. Maybe I'll absorb the negative, leave the 1/5 outside. I'll absorb that negative there. And now I'm ready to go. P inverse AP, right? That's what we need to get this matrix representation with respect to the non-standard basis. All that is 1/5 negative 2, 1, 2. That's P inverse. A, 1, negative 1, 1, 1. And P, sorry, P, negative 2, 1, 1, 2. And here we have it. We just need to perform some multiplication. Leave the 1/5 out front. Don't want to do more than I have to. And I'll multiply the last 2 matrices first. Multiply these guys. Looks like I get negative 2 minus 1 is negative 3. 1 minus 2 is negative 1. Negative 2 plus 1 is minus 1. 1 plus 2 is 3. Okay. Multiply the remaining matrices. These guys, what do we have? 6 minus 1 is negative 7. 2 plus 3 is 5. Negative 3 minus 2 is negative 5. And finally, negative 1 plus 6 is 5. Oh, let me check that first one. Negative 2 times negative 3 is positive 6 minus 1 is positive 5. I like that much better. Multiply the 1/5 through. There we have it. Very simple matrix that does this same transformation, T, that we described up here, the x minus y, x plus y. It just does it relative to this basis instead of the standard basis. Okay, so Let's write out what that means. Given a vector u in R2. And I'll say, let's say it this way. The coordinates of this image of u relative to the weird basis we found, or the weird basis we were given, we'll call it B. The coordinates of the image relative to B just equal this matrix A prime that we found times the coordinates of u relative to B. Right, so it would be whatever A prime is times the coordinates of u relative to this weird basis B. And remember, what we get out there is still coordinates relative to this weird basis B. So if you got like 1, 2 out, you'd take one copy of this guy and 2 copies of this guy, add those together, and that's really what T of u equals. Remember, we're dealing with coordinates. You don't want to directly confuse coordinates for actual images. The coordinates of the images. Okay. That is it for this section. Stay tuned for more in the next.